I'm pleased to be here with you today and to talk about my favorite subject. The context, oh, it is there, okay. Just a couple of notes here in terms of what we're talking about today. And it's to say, and I'll show you the progress, but fusion, in fact, is coming sooner than probably a lot of people think. And I'll bring out both the political as well as the technical aspects of that. And unfortunately, Canada is not part of it. The rationale for Alberta, in fact, because of what's happening in the world at large, it's going to become very important, and we're going to end up being cut out if we're not part of this energy game going forward. So the positive side is if we do get involved, there's some real opportunities for Alberta, and I hope to bring out just a few of them quickly. And it would involve in absolutely everybody, in fact, the whole country. This would bring in everything from the research and development, the technology spin-off, the energy implications, and a lot of intellectual property in the long run. Let me just get that up there. Now, I just want to remind you, we've got things cutting out here. Fusion is not fission. Some people have a bit of apprehensiveness about nuclear waste issues in fission, and please let me distinguish clearly between them. Fission works with the very heavy elements, such as uranium-235, where if I add a neutron to it, it forms a transient unstable state and immediately decays, releasing a lot of energy, and along with it more neutrons. Those neutrons can then in turn induce more neutron activated inducements here. And so you can have actually a runaway condition. And the issue is to control the neutrons so you just have a controlled system going forward. The issue that people are concerned about, of course, is the radioactive waste. And besides, I show these two daughter radionuclides, but there's cesium, iodine, and so on. In contrast to fission, fusion works on the light nuclei, and this is the process that occurs in the sun and all stars. In fact, fusion is the fuel of nature universally. And it works in the case of the sun. If you take ordinary water, H2O, the H part of it, the hydrogen, if I take that positive nucleus in the hydrogen, the sun is just a hydrogen burner. It takes ordinary hydrogen, just the H part, fuses with another H to produce helium and release energy. And that's how we get all our solar and all the other energy that drives everything on Earth. It's from fusion events taking place in the sun. Well, on Earth, we don't have the luxury of having that large amount of mass that the sun has in terms of getting reaction rates up to produce enough energy. So we have to try and look for a simpler way, and one of them is to use isotopes of hydrogen, one of them being deuterium. Deuterium is just a hydrogen plus an extra neutron, and tritium is hydrogen plus 2 extra neutrons. It turns out when these fuse, we get the helium and a neutron and energy release, but the probability of inducing this reaction is much better than just hydrogen on hydrogen. So on Earth, we have to try and do things technologically the simplest approach, so we work on deuterium and tritium rather than hydrogen and hydrogen. But the upshot is the same. Well, why do we want it? You are all increasingly aware of the importance of electricity, running our homes, our industry, all kinds of things now, even with mobile transport in cars, electric cars. And in fact, if you project through this century alone what new production we're going to need in electricity, apart from replacing existing power plants, the answer is, and it's a number that I will throw at you, don't worry about it, but 40 terawatts. That's a lot of power. That amounts to more than $100 trillion worth of economic business to build those power plants in this century alone. This is very big and very important. Well, if we're going to produce all that power, how are we going to get it? We can't keep burning coal. We've got the greenhouse gas emissions and climate change. The world is changing. It's turning off coal. We've got 3 possibilities. We've got fission, we've got fusion, and we've got renewables. And I won't get into all the details, but Renewables, we'll use them as much as we can, wherever we can, but they won't be a universal panacea for all the energy requirements on Earth. Fission, there we'd have to turn to breeder reactors because ordinary fission that works with light water reactors now doesn't have enough fuel to keep us going for the long term. Fusion is the one that is absolutely sustainable. It can go literally forever, and it's clean. It has no side effects that we have to worry about. Well, at the end of the day, once we've got fusion, we can do a lot of things. We can get process heat, we can get electricity, we can do a lot of other things like producing hydrogen, so it would open us up to being able to make use of fuel cells and so on. So if you add up all the reasons why you'd like to have fusion energy, it's a multifold of things. Virtually inexhaustible fuel supply. You have no greenhouse gas pollutions. In fact, helium is the ash of fusion. Well, helium gas we can take. Unfortunately, we won't produce enough to make up for the depleting gas field supply that we have right now, particularly in Texas. But it means you just can't have your grandchildren with balloons all the time. But in fact, it is going to be a main producer of helium. That's the ash of fusion. No long-lived radioactive waste, no risk of a nuclear accident that you'd have to worry about what happens outside the power plant. And an important thing, in fact, fusion is the highest energy density fuel available to us. Solar is the lowest energy density. We have to take a lot of land to collect enough. This is the other end. The general environmental impact is small. Let me illustrate that impact with this very telling slide. If I take a 1,000 megawatt electric power plant and ask how much fuel do I need to drive that plant for just one day, in the case of coal, I've got to supply about 10,000 tons of coal. Over the course of the year, that adds up to a train about 26,000 car loads long to deliver the coal to the plant. That's a very large amount of fuel. If I fire it up with a fission plant, it takes less than 100 kilograms, just over 200 pounds. If I do it in fusion, it would take 1 kilogram for a day or 365 kilograms for a year. That amount of fuel for a year can be delivered in the back of a pickup truck anywhere in the world. So the geopolitics are immediately reduced. Everybody can have access to it. Land and ocean is the source of deuterium. The seawater is, for every H2O in water, the D2O for deuterium is 1 part in 6,500. So we've got an infinite of billions of years of deuterium in the ocean water, and everybody has access to that. So you can see the dramatic difference then with all of the other stuff that you have falling out of coal-fired compared to what you would have in the fusion case. Well, why haven't we got it? We know the sun makes it work, and in fact, we already know, unfortunately, that the hydrogen bomb works as well, so we know how to do it on Earth, too. The question is, if I'm going to take these hydrogen nuclei and put them together, deuterium, tritium, they're positively charged centers, and we know that like charges repel. So I've got to give them enough energy to bring them sufficiently close together that they can actually fuse and create a new atom. To do that, to give them enough energy, that's the same thing as saying they've all got to be at a high temperature. Temperature and energy are the same thing. And it turns out the temperature you need is about 100 million degrees. That's obviously not a trivial temperature. Matter, at that temperature, matter is ionized. It's no longer neutral atoms, nitrogen or oxygen or anything else. It's all charged particles, positive and negative. We call that state, it's the fourth state of matter. Solid, liquid, gas, plasma is the highest temperature state of matter. It's called plasma. And it means then we've got to confine charged particles, because if I'm going to invest energy to heat them up to that temperature to start the reaction, I better get more energy out than I invested in the first place to make the whole thing worthwhile. So with the charged particles, I have to look at confinement. And there's a very simple parameter that says how much confinement you need in order to realize more energy out than you had to invest in the first place. And it turns out to be a parameter that refers to the density of fuel times the confinement time. It has to exceed a certain value. Well, you've got some play there. You can play with low density and long confinement time, or very high density and short confinement time. And that sets the way that we go about doing fusion research. One of them in the magnetic confinement case is to work with low density and put it inside, call it a hollow donut with magnetic field coils on it, because magnetic fields have the property of wrapping charged particles around them and trying to hold them from going somewhere else. So imagine a hollow donut with magnetic field coils on it, and I heat this gas up to a temperature that it's all charged, and it's running around the inside of that the inside of that donut, and then the fusion reactions are taking place, then I have to take that energy out. Well, that's the way magnetic confinement, and I'll show you the world's progress on that. That's been the longest study. It goes back to the 50s, and it's why is it doing that? The second approach is the one that's dear to my heart, the inertial fusion, and that's to say, what about if I could take a small pellet of fuel, very high density, and do all the dirty work in heating it and getting the energy out in a very short time? So in that case, you take a pellet of fuel, you irradiate it with some source. I'm going to talk about lasers that could very quickly heat that pellet up to ignition temperature to get the fusion reactions taking place, and then it burns up and you get your energy. And the way that would be sustained is you would have, it would be like an internal combustion engine, like we inject the fuel into a cylinder, ignite it with spark plugs, and get the thermal blanket coming out of that for a car engine. In this case, you'd inject the pellets, fire the laser beams, collect the energy, inject the particles, fire the laser beams, and you'd do it about 10 times a second. So it would be literally an internal combustion engine, totally under control. Let me talk about the magnetic, first of all, where we are. This device is called the Joint European Torus. It's located in the UK, funded by the European Union, and it's currently one of the largest tokamaks that's working in the world right now. The tokamak is, in fact, the most advanced concept in magnetic confinement. I haven't got time to take you into all the other approaches. It's a Russian invention going back to the late 1950s, and it's been pursued now for a long time, and the progress I'll show you in just a minute. This is the device that has been running for a long time now in the UK. It has actually produced 16 megawatts of power. This number Q refers to how much out over how much in, so it's not got to unity there. But ITER is the big new international reactor being built in Cadarache, France. It's an international consortium of about 35 countries. Canada isn't one of them. It's hosted by the European Union, so they pay 45% of the bill. It's a $20 billion experiment that's being built. And the rest of the contributing countries put in about, there's 9 in the distribution then. Whoops. Anyway, you get the size of it. There's a person, there's a man down at the bottom, and you can see the scale of this device that is now, the pieces are being built all over the world. They're being brought to France in due course to be assembled, and I'll give you the timeline on this in just a minute. But it gives you a scale of what's being aimed at. It's looking to get out 500 megawatts of power with this Q of 10, so 10 times output over the input heating power and a long confinement time. And so that's a very major undertaking at the present time. If we ask how much progress have we made in this magnetic confinement approach to get to the condition of burning hydrogen fuel, here's the promised land up here where we have to be. The 2 parameters we need are temperature. I show it here in kilovolts. This is 100 million degrees at that number right there. And this is the confinement parameter up here. You've got to get up into this region to make fusion pay off. These are the devices that have been built all around the world over the years, not all of them, but quite a few. There's JET in terms of what it's realized. This ITER project is taking us up into here. So we're looking for a net power gain of about 10, a real burning plasma. Here's the timeline. They're building it now. It's to be commissioned in 2022. It'll be run as a plasma experiment for about 6 years before they put deuterium and tritium in to achieve fusion burn. So let's say a 2028 period that we'll have real fusion power demonstration. And then they'll go on from there to design even an upgraded power demonstration unit beyond that with the technology that's been learned through this first learning curve. There's a number of other things that have to come along with it. I should say, incidentally, given that we're 2030 and 2040 periods here, China, and this is a key thing, China is not only contributing to ITER, but internally they have even larger working budgets to make fusion work at home. In their 5-10-year plans that you're aware that China regularly does, fusion is one of their 5 priorities, and they want fusion working for the 2030s. Now, China can turn on the manpower, the budget, and they do things very well and very quickly. They built one of these tokamak devices in 3 years that the Western world took 10 years to build. So they can really turn it on. So I expect a lot of the pressure, in fact, in the forward progress is going to come from China, India, Korea. Korea also has passed national legislation that fusion is part of the national agenda. It's in the permanent line item budget. Let me turn to inertial. It's the newer boy on the block. Lasers got invented in 1960. People started calculating right away, gee, could we ever use a laser to heat up a fuel pellet to get fusion conditions? And by the mid-70s, people were starting to build lasers enough to start doing the experiments. Indeed, I did in my own lab at the University of Alberta. But the calculations suggested if you could do it right, this would be a very interesting way to go about doing fusion. It avoids a lot of the complexity and the size of that tokamak that you just saw, the big ITER one. It's a huge machine. The idea here then is to take a pellet of fuel, irradiate it with laser beams or particle beams or X-rays or anything, and you would literally, it's like a rocket. You hit it, you produce a hot plasma that blows off, and old Newton's law says if I have momentum in one direction, I get it going in the other direction as a reaction. And what I lead is to shock compression to collapse this fuel pellet to a small dimension. Suddenly all the energy collapses at the center and you get a spike in temperature. You reach your 100 million degrees to ignite, and then the helium that gets produced as a byproduct, that helium energy gets reabsorbed to heat the rest of the pellet, and you burn up the fuel pellet. The output then is heat and helium, and you would generate your electricity and so on. Here's the state of the largest facility in the world that's operating right now. It's the National Ignition Facility in the US. It's in Livermore, just inland from San Francisco. And that's a view of the building. This is a cutaway view of that facility, and I want to pick up 2 points. These are 4 clusters of high power laser beams, and the beams come and they all get focused on this target chamber down here, and that target chamber is 10 meters in diameter, so 30 feet in diameter where they have the pellets. This was designed and built on 1990s technology. It became operational about 2009. And so it's all old flash lamp pump technology to pump the laser system. We now know how to do this with solid state lasers, light emitting diodes and so on. If we built this thing today, it would be 1/10 the size, 1/10 the footprint. And it would be more efficient, more reliable, and all the rest of it. So a lot of progress says we know how to go forward from here into the next generation. This is a view inside of, there's 2 of those clusters. There's 2 people standing there, so you see the size of that existing facility. It's very large. There's a lot of energy in the laser beams and very high power, 500 terawatts of power, and that's a view inside the target chamber. Well, here's the progress to date. So bear in mind, this research started 25 years later than the magnetic fusion, but in fact, it's caught up. Here's where the results from the past experiments are on magnetic fusion. Here's where ITER is going, and here's what this laser facility has done already. We haven't quite reached the promised land. We're about a factor of 3 away in the critical parameters, but you can see it's very close. And to any engineer who looks on a logarithmic plot and sees where you are, you can't say how long it's going to take to get there, but you can say for sure you're going to get there. So there's a lot of confidence in that. So it's been a remarkable achievement that this new approach, starting 25 years later, has indeed caught up. And it has a number of attributes that would say it could be a very nice way to go about building your power units, and I'll come to that in a minute. So that facility is in operation doing single shots. Eventually, you've got to make that into a repetitive one. I mentioned an internal combustion engine, inject pellets, fire the laser beams, and do it repetitively. So the next step is to do what they call LIFE, for laser inertial fusion energy. And this came about because Chu, when he was the Secretary of Energy in the US, told Livermore, don't wait for your scientific break-even before you start designing towards doing a demonstration power plant. And that's what LIFE was all about. They went out to the industry for supply of everything you'd need, what has to be developed in what time frame. Parsons Engineering and others in terms of all of the attributes, the utilities in terms of what they want or don't want with power plants and so on. And so they could do a full risk management analysis of what would be required in the approach to take them. Interestingly, if we had that scientific break even today, we're a factor of 3 off, but if we had it, the life was projected that in 10 years, we could have a power demonstration unit. And out of that, about 60% of the procurement would be off the shelf. You could go out and buy it today. About 30% would be scaling up in manufacturing. If you imagine semiconductor and other things where you've got certain capability, but for the demands of what you need, you've got to scale up that manufacturing. But that can be done short term. And then about 10% would be the long-term enabling technology, new things that have to be improved on, but which for a decade would be a realistic time scale. So this is where that time frame came from. This is what a system would look like. Well, maybe. So you'd have your chamber, you'd have your injection power. You'd, first of all, produce your deuterium tritium fuels in the form of pellets. I'll say a word about that in a minute. Inject them, and we know how to do that. And you time flight them, so when they get to the center, you'd fire the laser beams, because these are all very short pulse systems, in the billionths of a second. You'd have your multiple. This is one of many laser beams that would be pointing in there. When the fusion reaction takes place, it gives you neutrons and helium. The helium would self-heat the pellet before escaping and collect it externally, and the neutrons would come out, and you'd have a circulating lithium blanket. And why do you want lithium? For 2 reasons. The neutrons react with the lithium to produce the tritium. Tritium is not a natural isotope on Earth. It's man-made. So you would extract the tritium generated by the neutrons with the lithium, process that to produce your fuel cycle with the targets, and then the lithium would go into your standard thermal cycle, your heat exchangers and electric generation and so on. Okay. This is a conceptual view of what that plant would look like. The footprint of this would be, if you imagine your coal-fired plants or anything else, a fusion-fired power plant would be essentially the same kind of dimension overall. The target chamber is in the middle. This was designed on the basis that if I had things like silicon carbide, I would have absolutely 0 radioactivation, and I'd love to build it, but I don't yet know how to build silicon carbide in very large quantities. And engineers love to build things out of stainless steel. So they designed it around stainless steel because that's something we have to work with today. And the approach was to say, let's have 2 target chambers. I put one into the system, and when it gets radioactivated a bit, I pull it out and put another one in. So I keep the power plant going. I can then reprocess the first one and put it back in the system again. It was a very nice engineering solution to what could otherwise be an issue. Let me turn to Alberta. In terms of how this would impact us, not only energy, because it's going to be coming whether we want it or not worldwide, we should be part of that, that game. But secondly, there's just tremendous technology opportunities that come along with it. And I've just given a listing here of the few of the impacts. Lasers themselves are they're ubiquitous, as you know now in the world. Here's one right here. But for processing, automotive manufacturing now relies on lasers to do most of the welding and cutting and so on that's going on. Photonics, a word there, Europe did a major assessment of photonics. This is using photons to do work instead of electrons. We think of the world of electronics that came along after the 50s invention of the transistor diode and so on. The world of photonics is now taking over in everything. A study 3 years ago in the European Union, commercially, photonics was already bigger business than electronics, and it was growing at twice the annual growth rate. This is very, very important for the future. It's everything from sensors, instrumentation, computer modeling and control. These plants are intended to be manufactured, not like one-off construction systems of existing power plants where you do everything on site. This would all be manufactured, delivered on trucks, and assembled. So it's a very different approach to doing fusion power plants. Okay. Just to pick on a couple of the technologies, here's the flash lamps that are used to power NIF. This is the modern world of solid-state light-emitting diodes that have increased efficiency, reliability, all the rest of it, cost, that will take over into the future generations of these laser systems. This is something you wouldn't recognize. You think of ceramics as being opaque, that we can't look through our china cups and so on. A little company in Japan went out and said, we'd like to have transparent ceramics because they would be important for laser systems that have to be able to transmit light, obviously. But we like ceramics because they take have much higher temperature characteristics and handle more heat than ordinary glass and so on. And this company learned how to make transparent ceramics. Well, this is going to revolutionize the way we build high-power laser systems. And a final thing here, before I throw up a summary, an economic impact study in the U.S. looking at the U.S. only for the fusion procurement, looked at the job creation and the build-out of how it would look at manpower-wise. And they predicted for the U.S. supply alone, it would have an economic impact of the same number of jobs as things like aerospace, semiconductor manufacturing, machine shops, and so on. So it's going to be big. Well, this is, I'll leave this to, you can ask me in the questions after about where could Alberta fit into this. Let me come back to that. So the summary is, fusion is coming. We have an opportunity to participate in it or stand back and then buy it from the rest of the world. But in 50 years, we're not going to be selling oil and gas to the world because they're going to have these alternative energies and be independent, and we have to prepare for that. In a decade or two, we can have the fusion power plant demonstration. Canada, so far, is the only developed country that's not involved, and we need to change that. And we have very strong links, as it turns out. I've spent a lot of years as a consultant in the US, Europe, and Japan, and we have good working relationships that if we want to start building and collaborating, they're quite happy to work with us and give us that opportunity.